Hello, Jeff Disher here again. Today I'm going to be talking about data compression. So first of all, why would we be interested in compressing data? What can we actually get out of it? What's the cost involved in doing this? What are any other sort of weird upsides or downsides? What's the difference between things like lossy compression versus lossless compression? And how do we look at compression differently for things like text or programs versus things like video and audio? First of all, why would you want to compress something? Well, the obvious thing is just to make it smaller. If a file you have is several gigabytes in size and you find some way that you can change the way you look at the data such that it now becomes several hundred megabytes maybe, this is an improvement because of things like storage. But it can also have interesting other upsides and downsides. First of all, compressing things and decompressing them usually ends up being somewhat CPU intensive, so there's often this idea that you can't actually use the data that's compressed immediately. Now this is not entirely true, it kind of depends on the situation, but it is something that you do have to be generally aware of, and this is something you can see a lot if you look at, say, video, for example, where spending time compressing video is still very CPU intensive, and as we get larger screens and larger video sizes in terms of just physically how big they are on the screen, this cost is increasing continuously, even though we're getting better CPUs and better GPUs for it. So now that we know why you do it, well, how does this actually work? What are we trying to do and how do we get there? Well, fundamentally, compression is about trying to find patterns within data, because if there's patterns within the data, you can come up with a more concise way of phrasing that entire pattern as it is and say, oh, that's just pattern number 7 or something, instead of actually having to record the entire thing. Now, there's different ways that you can do this and different kind of implications in terms of how you want to think about it, but that's kind of the gist of where we're going. It's worth pointing out at this point that there's a huge difference not just in the actual implementation of a given compression algorithm, but even in the philosophy of what problem you're trying to solve with it, because there's different situations where you might need to compress differently. For example, you might have lossless compression for certain things and lossy compression for others. So lossless is a pretty obvious one. You don't want to lose data when you actually compress the data. You want it to still look the same when you decompress it later. This is common for things like maybe you have text. You don't want your manuscript you're compressing to send to someone to, when it's decompressed, well, some of those words that didn't come up very often, we'll just replace those with more common words. No, you've actually now changed it. It's no longer relevant. It's no longer valid. We can't lose information when we actually compress and decompress lossless compression. This is another big issue when you look at things like programs. A lot of programs, especially in certain language environments, they're actually compressed all the time, except when you're about to execute them. Well, if the instructions changed when you decompressed it, it really wouldn't work. Instead of saying, oh, add 2 plus 2, it says, call this weird function that doesn't exist, or something like that. Like, you cannot change it. That's why in many situations we end up with lossless compression, because we actually don't want to be changing anything. However, this is not true in all cases. Now, lossy compression might seem to be sort of a confusing idea. Well, why would we want to lose data when we're actually compressing things? Like, we're losing information now. When we decompress it, it's not going to be the same. How could this possibly be a good idea? And the answer is because in some situations you didn't actually need all the data. Remember, in something like a text file, the correctness is going to be the correctness of every word. But in something like an image, well, it just needs to mostly look like what you started with. And this is why things like JPEGs, for example, can compress very well, partly because they're throwing out information as they go, because they're not trying to get 100% fidelity reproduction of the input data when decompressing. They're most interested in making it small and basically deciding that it's more or less equivalent to what you started with. It might be a little different, but it shouldn't be too bad from the perspective of someone looking at it. Of course, this isn't true in the case of all image compression or all audio compression or all video compression. While generally speaking, we tend to allow for lossy compression of those file formats, some of them are lossless. Like, you do get things like in static images, things like GIFs or PNGs, those are lossless encoders. When you're looking at audio, you can have things like FLAC, and that's a lossless encoder as well. But for the most part, we typically have lossy encoders because they make the files much, much smaller. Now, where would you go if you wanted to do more of a deep dive into some of the technical details of how some of the compression algorithms actually work? Well, when you're looking at lossless compression algorithms, you often end up looking for things that are derived from either a Huffman coding or Lempel-Ziv encoding. Now, these are two completely different ways of basically just trying to find patterns to make things smaller. Huffman coding is based on the idea that within your actual input file, there's going to be certain pieces of data which occur more often than others. So, say you have a text file, well, encoding every letter as one byte might be kind of wasteful what if 90% of those letters are E's or something like that? Well, you can just look at the data and determine, all right, well, here's the probability that we're going to see any given letter. Here's their statistical distribution within the input. And just say, okay, well, the smaller ones will be maybe 2 bits long instead of 8 bits that you normally see in a byte. And the really uncommon ones, well, we'll kind of run out of efficient encoding, so maybe they'll be like 12 bits or something. And because you are going to have much more of the smaller ones, the file ends up being smaller when you actually do this re-encoding. Now, Lempel-Ziv encoding is actually based on taking this problem from a completely different angle. It's still trying to find patterns in your data, but not within data elements themselves. It's actually trying to find patterns between data elements. So, for example, you might say that, oh, these two letters seem to occur one next to each other a lot. Well, let's just treat that kind of like a new kind of letter. And you can build this way of encoding things over time as you're encoding or decoding the actual Lempel-Ziv stream. Now, this is common in what you'd see in like zip programs and things like that. And it tends to work very, very well for certain kinds of data. For example, text. It turns out that when you're writing a language, there's a lot of patterns. Words like the come up a lot in English. So it tends to make things a lot smaller when you realize that it's really about phrasings of data elements, not data elements themselves. Not all letters are created equal, but also not all groupings of letters are created equal. So this actually ends up getting really, really good compression algorithms in lots of data formats, mainly things related to text or XML, something like that. Now, last thing I want to talk about related to different kinds of compression algorithms is a numerical transformation. Now, this is a much more complicated way of looking at it, but this is relevant when you look at how things like video or audio or images could be compressed. In these cases, you're actually trying to determine what the patterns of different pieces of data within the input are, and which ones are important, because you can determine then, okay, which pieces of data should we encode? How should we encode it? So, for example, if you're looking at, say, a JPEG, you're going to be using a cosine transform. Some video formats and image formats use things like wavelet transforms or Fourier transforms. And these things you could actually look up if you wanted to find out the greater detail in them, because they are incredibly complicated from a numerical computation perspective, but you would often end up learning about things like this in probably third year university if you were to be taking this, because that's when they start talking about certain numerical methods and things like that in computer science. It's interesting stuff, but very, very complicated and hard to remember. This brings us kind of full circle to, okay, now that we know basically some of the ideas behind this, well, what are the real trade-offs involved here? Because remember, if we're having to do things like, well, we've compressed the data, which now means when we want to work on it, we have to decompress it to actually start operating on it. Well, isn't that going to be slow? And the answer is, usually it's not, actually. And this is for a few reasons which are kind of interesting when you remember, wait, what the computer is actually doing. So in a lot of cases, you're going to be doing something like, oh, I'm getting a web page from the internet. Well, a lot of web traffic is actually transparently being compressed for you by the web server and decompressed by your web browser. The reason for this is it makes it a lot faster because the network is slow. So if you have to send a megabyte of data over the internet, that's going to be a lot slower than 100 kilobytes. So for reasons such as these, you usually end up seeing a lot of compression used in those cases all the time, just because it always ends up being a good idea. But it's not just an internet thing, there's other things too. What about, say, the files on your disk? Remember, unless you've got a really high-speed SSD or something in your computer, your RAM is going to be way, way, way faster than actual disk access is. So, well, it would really be time-consuming if I had to read all kinds of disk blocks off the disk and do all the seeking and the waiting for it and the reading and all that. Well, what if we compressed everything all the time? So now, well, I can't ever just directly read a file. I always read it into memory, and my operating system transparently decodes it for me because, oh, that turns out it was a lot faster. Not only does it use less space on the disk, but now instead of having to read several different sectors of the disk into memory, I just read a few of them. And then once it's in memory, I can quickly do the decompression because that just uses some CPU time and a little bit of memory. It doesn't actually wait on my hardware to actually physically move disks around and things like that. And this is something which is becoming more common these days. For example, if you use BtrFS on Linux, which I use on most of my systems these days, you can enable transparent compression on everything. And yeah, not only does it make things a lot smaller, but it also tends to make things a little bit faster. So it's kind of an interesting upshot. It's not a trade-off between small versus fast. Sometimes small is the best kind of fast. And compression, in a lot of these cases, can show that. Now, one of the last examples of where we're using compression in sort of new and clever places that I just wanted to sort of end on here is in what's called compressed memory. Now, that's going to sound confusing at first. What exactly does that mean? Well, remember, your computer has a certain amount of RAM in it. And once it runs out of that, it has to either fail to do new things, which on a desktop or server system we typically don't want, although you may have that in a portable device. So instead what it has to do is write out the unused memory onto the hard disk, which takes some amount of time. Well, we already have the data in memory. What if maybe we treated it a little bit differently? Instead of going all the way from it's either in memory or it's on disk, what if we said, oh, it's in memory but compressed? And this is something that a lot of operating systems are doing now. I know in, say, OS X, they have that idea. If you look at it in Activity Monitor, it's actually called compressed memory, and it tells you precisely how much of your RAM is compressed right now, which is kind of neat. On Linux, it's referred to as zram, I believe, and that kind of works the same way. You give it some limit of how much you want it to actually use for its kind of compressed swap. And instead of paging out to disk, it'll just swap into compressed memory by compressing the actual contents of RAM itself to free up more space. This has an interesting upshot as well because it means, well, okay, what if you compress a bunch of your memory and you're still full? You still can't find enough memory to keep running new things. Okay, now we have to swap it out to disk. But you know what's really cool now? We're swapping out something we already compressed, so it's even smaller. So this is really neat because you can have a lot of advantages within these systems just by sort of realizing this interesting cleverness of small can also be fast. And that's really where it comes from. So anyway, I hope that video was informative and kind of explains some of what compression is, gives you some ideas about where you could go for a deeper dive if you want to really understand the technical meat of it, but also explains why compression might not be a cost for you. In many situations, it's just win-win-win. All it does is make everything better on every level, which is kind of interesting. It allows you to just have your cake and eat it too, if you know that that's going to be how the situation works. And over time, more situations will be coming like that. So it's kind of interesting to be aware of because it gives you some neat advantages. Anyway, thanks for watching, and leave a comment or get in touch with me if you had any questions relating to this video or other suggestions for future videos. Thanks. Bye.